Hello everyone, this is 5.2a. Recall, invest 5,000 into an account compounded continuously at 2% for 5 years. We would use this formula. Continuous, we put that E there, remember? Future value is P naught E to the RT. P naught is our investment of $5,000. E to the 0.02 because it was at 2% for 5 years is $5,525.85. Okay, well, we're going to learn something new. Suppose instead of a one-time investment, we want to deposit $1,000 per year into this account. So that's the difference per year. Okay, so we're continually depositing and the money's growing. So we have a formula for this. It's future value constant continuous money flow. And here's the formula. Future value is S divided by R all times E to the RT minus 1, where S is the constant deposit. So let's do an example of this. Okay. So let's say S is going to be $1,000 like we mentioned above. So that's an annual deposit where T is 5 years and R equals 0.02. So the same problem as that, but this one we're going to be depositing once a year, $1,000. So we use the formula future value equals, and we put 1,000 in the S, divided by R, which is 0.02, E to the R, 0.02, times 5 minus 1. Okay, this equals 50,000. And when you do all of this, and I always recommend when you're dealing with money, especially large sums of money, you want to take your decimals out all the way that your screen will show you in your calculator. Okay, and you'll have less round off error that way. So when we multiply that, we should end up with 5,258 and 55 cents. Okay? All right, let's do another problem. We're going to be utilizing this formula again in our next problem. Okay? And later we're going to have one more little project to do. It'll be after our next lecture. But it considers all this stuff that we're learning. Okay, so here's another example. All right. Let's say there's a present for a 1-year-old from their grandparents. Present to a 1-year-old. Okay. And the present is at 18 years old, they'll get a fund. Okay. And what the grandparents did, they decided that they're going to invest $2,000 per year. At 5% compounded continuously. Okay? All right, so the question is, how much will the child have when they turn 18? How much will the child have when they turn 18? Okay, well, we know we see compounded continuously, and we know that they're investing per year. So that's how we know we're going to use the formula we just used. Okay, the investment is $2,000. The rate is 0.05, e to the 0.05, and then they're going to turn 18, and it starts when they're 1, so 18 minus 1 is 17. So over here we're going to put 17 years minus 1. Okay, so this right here is 40,000. Once again, you may want to practice on your own to make sure that you take your decimals out far enough. I generally take them out 5 spaces, 1, 2, 3, 4, 5. That usually catches most round off error. But you can go all the way out to the end if you want. 53,586. So you can check your work, make sure you're getting that. Okay, let's do another problem. All right, suppose you want $1 million when you retire. In 47 years. Okay, the question's going to be, how much do you need to deposit? How much do you need to deposit? What am I going to say? How much you need to deposit? You're right, per year. In a fund that pays 6% a year, compounded continuously. I'll abbreviate that. Okay, so you try her in 47 years, you want $1 million when you're done. How much do you need to deposit per year in a fund at 6% a year, compounded continuously? All right, so this is a bit different from the other one because here we knew the deposit and we found out the future. In this one, they're giving us the future and we're looking for S, the amount we're going to deposit. Okay, so let's write that up. So we know we want $1 million, and who doesn't, right? We're looking for S. We know the rate is 0.06. E to the 0.06. And that's in 47 years. And don't forget that minus 1. Okay. All right. Well, we're solving for S, and we can calculate all this out right here to be 15.77685. All right, and I'm going to leave S here, and then it looks like a 5. It's really an S. I'm going to divide that by 0.06 because there's the 0.06 right there. Okay, that equals $1 million. Okay, this divided by that is going to equal 262.9475. All right, we got $1 million over here, and we all know how to do algebra at this time. Divide by both sides, and we're going to have S equals, don't forget that dollar sign, $3,803.4 per year. Okay, I think that's pretty neat to be able to figure that out, and I wish I would have known something like this way back when. But you do now, so you can be wise with your money as you start making it. Okay, we have another formula. Here we go. It's accumulated. Forgot that U in there. Accumulated present value. Constant continuous. It's kind of a long title. Money flow. Okay, so this is going to be another formula. Okay, and here it is. We call this APV, accumulated present value, equals D over R times 1 minus e to the negative RT. So this looks different than what we've been used to. Now what D stands for? D equals the yearly payment. Okay. All right. I'm going to have to erase this so I can write down the actual question. All right. Okay, so here's an example. What would the grandparents have to deposit now as a lump sum? So what would the grandparents have to deposit now as a lump sum instead of depositing $2,000 a year? All right, to get the same results. Of $53,586. Okay, what would the grandparents have to deposit now as a lump sum instead of depositing $2,000 a year to get the same results of $53,586? Okay, so we're going to use our formula of APV. All right, 2,000 over 0.05 equals 1 minus e to the negative 0.05 times 17. And when you do all that work, the answer is $22,903.04. Okay? All right, now note, if you wanted to check this out, this is something interesting to see. If we take this amount, 22,903.04 times E, which is this formula, we are really familiar with this formula, 0.05 to the 17, we will get 53,586.